Now we are recording the lecture. So you can like screen capture in progress. So hopefully it's capturing the screen. Okay, you can pause it here and try to. But anyway, I'm going to upload it. So let's go to physiology. Okay, we were stopped here. Okay, I told you we were talking about the differences between anatomy and physiology in how we see the human body. When you start studying anatomy, you study the anatomical position of the body, the different cavities, the planes, okay, what organs are in which cavity of the body, then the relationships between different organs. For a physiologist, a human body is simply two big compartments, intracellular and extracellular. Okay, and this extracellular compartment is subdivided into two subcompartments, which are the plasma, okay, inside the blood vessels, and the interstitial fluid. This is how a physiologist sees the human body. Okay? And then we study, and everything is surrounded by a barrier. That is the skin. It's called the tegument. Okay, so it's a lot more simple, okay, how we see the human body than how anatomists see the body. We also study the movement of different substances, okay, from the outside to the inside, from the inside the body to the outside. Okay, all these ins and outs, inputs and outputs need to be matched. Okay, we don't have any excess or defect of a substance moving in and out. Okay, we have excess of things going out, something wrong is going to happen. If we have excess of material going out and we don't replace it, also something bad is going to happen. We also study the movement of substances between the compartments. Okay, how the intracellular compartment is made, what is the composition, and what is the composition of the extracellular, and how they exchange material, what are the mechanisms that allow movement of materials between the blood and the interstitial fluid, and between the interstitial fluid and the fluid inside the cells. And we study also what processes require energy, okay, to produce this movement. Okay, and how we get the energy, where we get it from, how we store it, how we transform it. Okay, all of this is are the things that we study in physiology. Okay, we study gradients. Okay, how we generate gradients that allow the movement of sodium from one compartment to another, or potassium. Okay, all of these concepts to later understand the function of the body. We study also the flow of information. For example, information can travel from the nucleus of the cells. Information of how to make a cell is inside the nucleus. Okay, and then that information flows outside the nucleus in the form of RNA. Okay, we have the information stored in the DNA. Okay, we take a little piece of that DNA and transcribe it into RNA that goes out of the nucleus, and that information goes to the ribosomes, and the ribosomes make a protein, and that protein does something. That is information flowing from the nucleus of the cells to make other cells, okay, or to do other things. Like, for example, some of these proteins may stimulate other cells to grow, or other cells to produce a hormone. Let's say you want to produce thyroid hormone. Okay, the thyroid gland normally doesn't start making thyroid hormone. Okay, there is a cell in the hypothalamus, okay, that sends a signal. So in the process, DNA, RNA, protein, that protein goes from the hypothalamus to the anterior pituitary and binds to a cell there. That stimulus activates the DNA in that cell. DNA, RNA, protein. That protein, that is called thyroid stimulating hormone, goes to the blood, goes to the thyroid gland, knocks on the door, binds to the receptors there, and starts a signal that makes that cell in the thyroid gland, DNA, RNA, protein, so we make thyroid hormone. And then thyroid hormone goes back and tells the hypothalamus and the pituitary, hey, no more signals, I'm fine, okay? That is what we call negative.
It's called what?
Negative. Okay. And also does the thyroid hormone, all the actions that thyroid hormone does. Okay. If you learn that concept, you practically have the 50% of the physiology learned. Okay. All this mechanism of negative feedback. Okay. How we maintain how we regulate the amount of hormone that we secrete, the levels of the hormones in the blood. If you learn all those concepts, then physiology becomes boring, because everything is more or less the same. Okay, and then the same in pathophysiology. If you study inflammation, then the rest is boring, because almost everything is inflammation of different things. But it's like if you study fire and you start using fire to destroy a computer, okay, or phone, it's fire, burning things. Okay, but we are burning different things. Yes. So, well, we were talking about the compartments. These compartments have water and electrolytes and proteins and different chemicals, organic, inorganic chemicals. Okay, they are different in composition. Okay, the intracellular and extracellular compartments are very different. Okay, and the extracellular, that is subdivided into plasma and interstitial space, they are more or less similar. They have just some important differences, but they are more similar than the extracellular and the intracellular. Notice that most of our body is water. Okay, around average in the general population, the average composition is 60% water, 40% solids, solid material. That varies according to age, according to sex. Okay, we are going to be learning how to roughly calculate the water deficit in a person. Okay, roughly I say, because we always either overestimate or underestimate the amount of water that a person needs when they are dehydrated. Okay, that's why when you work in ICU or you're working in hospitals, there are more sophisticated devices, formulas, okay, to give the person the exact amount of water that they need. Because here we have an average man and a woman, okay, and if we calculate the water composition at 60% or 50% for women, that is just for the average person that weighs 70 kilograms and has a normal amount of body fat. Because if you have a person that is obese, for example, the adipose tissue contains very, very little amount of water per cell. Okay, so you have to, instead of using, for example, 50% for a woman, you're going to use 40%. And that is roughly. And if the person is very skinny, imagine a marathon runner that almost has no adipose tissue. That's muscle, everything. Instead of 60%, you're going to use 70%, okay, to calculate the water. Because everything depends. The muscle cells have a lot of water, and the adipose tissue cells have almost no water. So we have to adapt. Here we have a representation of the different composition of these fluids that we were talking about. Okay, compare, for example, the intracellular and extracellular compartments. Okay, notice the first thing that calls the attention, okay, what is in blue there. Okay, sodium. Sodium is present in a very important amount in the extracellular compartment. No need to memorize numbers here. Okay, just huge amount. What is the most abundant electrolyte? Sodium. Okay, you're going to learn the normal values later in clinical medicine. Now, if you go to the intracellular compartment, notice that the most abundant cation is potassium. Okay, potassium. How do we maintain sodium there and potassium here? Who can tell me? Sodium, potassium pump. Every time. That is like an immigration officer there. Okay, we have to control how many people go out and how many people come back. We say an immigration officer in some countries, in Cuba, for example. Here, no, here it's more like, gonna go out, bye. But in Cuba, they control very well who is inside, who goes, for how long. That's crazy. So every time, okay, sodium dares to go out, it's gonna be taken back. Okay? Notice that sodium is going backwards against a very high concentration. From a very low, what is sodium here? Oh, I almost don't see it. The concentration of sodium here is 11. Here, 145. You need a lot of energy to push, okay, sodium there. The same happens with potassium. What is potassium? 5. Okay, you need to take it back into the cells against a concentration of 135. That requires energy. And you see this very simple, and I'm sure you know this very well, because you have studied biology, you have studied anatomy, physiology, you prepare for the entrance exam. But sometimes these very simple concepts, when we make questions, students miss them. Okay? Because you know that this needs energy, and that needs ATP, which is the currency of the cell. So if you see a question that says, for example, which of the following will happen if the cells don't have ATP? You immediately will recognize that potassium will stay here, and sodium will stay here. So people are going to develop a hyperkalemia. No? Potassium is going to increase, and sodium is going to increase here. Now, what happens next? What do you think will happen if sodium increases from 11 to 50? What will happen with water? It will go into the cells. So the cells, after they don't have ATP, start swelling. It's the first step before cells die. Because when that happens, all the organelles that normally are like this start separating. Now, the nucleus is here, the endoplasmic reticulum here, the mitochondria here, the lysosome there. So, where is my mitochondria, the one that gives me? Okay. Cells can work in those conditions.
Is that hypotonicity?
Is that?
Is that hypotonicity? If the cells...
Well, what we have there is that you are increasing the sodium, the osmolarity inside the cells. And this sodium attracts water. Okay? And cells swell. See how those concepts apply. Now, that's a question that says, what happens if cells don't have ATP? But then we can create a question that says, 20-year-old, blah, 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 feels very tired every time he or she practices sports, it's muscle weakness, and genetic analysis shows a mutation that affects the mitochondrial DNA. Which of the following is the most likely mechanism of this condition? Poor oxygen utilization, okay, excessive CO2 in the blood, different things. But we know that the mitochondria are the ones that make ATP by using oxygen and glucose or fatty acids. So that's the response. Okay, a person goes under the sea and gets rid, the oxygen is off of oxygen, doesn't have oxygen. Which of the following will happen? Well, if there is no oxygen, there is no ATP. And that process will happen. So try to see the connections between the different things.
So, Dr. Diano, so the portion that you said no ATP is like you said, anything that blocks the sodium potassium ATP.
Exactly. Lack of oxygen or cyanide intoxication. You're going to be learning different mechanisms that impair the working of the mitochondria, impair the utilization of oxygen, impair this.
Professor, you said so if the pump stops working, sodium's going to increase inside the cell.
Yeah, the cells, remember the sodium potassium pump, what it does is take sodium out and take potassium back. If that stops, okay, mind that you can only allow 3 people from nursing to enter into the room. Every time there is a 4th, someone is going to take that student out. Now, that person says, I have to go to the restroom. 4, 5, 6, 7, 8. There's no one that stops that from happening. And once we have those certain amount of nursing students, 20, then maybe ultrasound students start coming, oh, look at this, that is a pipe. That's water. Okay. So this is the way we see the body in physiology. That is our anatomical position. Okay, that's the human body in physiology. Where we have the intracellular fluid. Don't pay attention to numbers. I'm not going to ever ask you about numbers. You can find 60, 57. That's depending on the book that you're using. Okay, what we have inside the cells? Lots of potassium. Okay, we have calcium, we have phosphate, we have proteins. Okay, we have organelles. For example, calcium, this is why I put the smooth ER. Calcium may be in the cytosol and also in the smooth endoplasmic reticulum. Okay, we have lots of calcium in the smooth ER. We need to activate the enzymes. We release calcium and then we take it back. We need to contract the muscle. We release calcium and then take it back. Also against concentration. There is another enzyme, pump here that is called the calcium ATPase. That also takes the calcium back using ATP. Okay, we are going to be seeing the importance of these concepts. Now, this is the extracellular compartment. Okay, subdivided into plasma and interstitial fluid. The most abundant electrolyte here, sodium. Okay, we have there also bicarbonate. Okay, we have some chloride too. That means sodium may be in the form of sodium bicarbonate or sodium chloride, different forms. Now, what is important to understand from this slide? These two compartments here, the plasma and the interstitial space, they are in what we call chemical equilibrium. Okay, the chemicals, the electrolytes, if you compare the concentration, they're almost the same. Okay, there is a small difference. If you go back to the previous slide, you're going to see that there is a small difference. For example, okay, you have the, where is it? You have the sodium, 140, 145, chloride is 104, 117, but they are more or less in the same amount, chemical equilibrium. Why they are in a chemical equilibrium? Because the barrier that separates the plasma from the interstitial fluid is leaky. So we have there the endothelium of the capillaries. There are spaces in between the endothelial cells that can be tighter or wider depending on what organ. But normally electrolytes pass freely, okay, from one part to another. Okay, now besides the endothelium, under the endothelium we have what we call the basement membrane. What is a barrier? Okay, a barrier that will stop any cell or any protein, okay, from moving towards the interstitial space. Here we have, for example, the blood proteins. We have albumin, we have antibodies, we have different enzymes, different things that we want to keep them in the blood, not leak into the interstitial space. Okay, but electrolytes, they move freely. Calcium, sodium, potassium, chloride. Now, there is another equilibrium that is a bit more difficult to understand. It's the dynamic equilibrium, also known as dynamic constancy. Dynamic constancy. It's constant, but dynamic. No? And this is the concept that explains that we have two compartments that are maintained in a relatively constant size and with relatively constant compositions, even though they are totally different. Okay? How we get that? Simply by using this. Okay? That is the secret of why we are alive. While that is working, we are going to be fine. When this stops working, we are not going to do anything else. Okay? And just in 1 minute, if that stops in the brain, we are going to be unconscious immediately. Okay? That's what keeps the difference between the intracellular and extracellular compartment. If that stops, then the cells are going to swell. Okay? The membrane, for example, of the endoplasmic reticulum are going to burst, are going to break down. All the calcium is going to be released. The calcium is going to activate enzymes. The enzymes are going to start breaking down everything else, and the cells die. Okay, so that's what keeps us alive. That needs oxygen, that needs glucose. That's why we breathe. That's why we eat. Okay, to maintain this thing working. Okay, what separates the intracellular from extracellular? The cell membrane. That we are going to be talking more about the cell membrane. Okay, it's a selectively permeable membrane. Okay, it's only permeable to substances that don't have electrical charge. For example, alcohol is capable of moving oxygen, CO2. Now, if something has electrical charge, not allowed. Only through specific channels, through specific transporters, when the cell decides, okay, while the cells are working properly. Okay, in disease, we are going to see that this thing doesn't work properly.
So the cell membrane is like a barrier, basically.
Separation between the intracellular and extracellular compartment. Well, let's have a break. Okay, it is 11. Let's have a break until 11:15. Okay, we're going to have 15 minutes. We're going to see this with examples now what we continue studying. For example, an action of the mirror. Okay, if you want to transmit a signal from here, the point 1 to the point 2, okay, you do it by using action. You open some channels. There are sodium channels here. Sodium goes in. Now you have an increase in sodium here. That increase in sodium will open other sodium channels. Now this sodium will open another. And then, okay, do you remember the action potential? It has a depolarization and then a repolarization. The repolarization is, but the depolarization is because of the increase in positive charges here. Goes towards the positive. Then you need to take it back to the negative. But how you do it? Not by taking the sodium out, it's by taking potassium out. Okay, now you have excess sodium inside the cell, excess potassium outside. Transmitting force here. Now this area is going to remain like this for a while, but then we need to take the sodium out and the potassium back in.
It's kind of like breathing, right? Like the same, like when
you can, if that works for you.
Right.
It's okay.
Thank you.
A quick question. Here, I
goes down, so still steady state. I wrote down that steady state there isn't necessarily a ranking. I read it, but now that I learned about it,
In a steady state.
yeah, in the steady state. And then same with equilibrium. I know there is no transfer because everything is equal.
Okay, what is the steady state? You have here two compartments. Okay. One has sodium, potassium. Let's say every minute you lose 10 particles and gain 10 particles. Okay, so there is no net. Net means amount lost minus amount gained divided by net means amount gained minus lost. You gain 10 every minute, you lose 10 every minute, so this is 0. The net change of the substance is 0.
Okay, and that's exactly what's happening. I'm saying.
The important thing more than the concept, because the concept is very abstract, is remember the steady state requires energy, the chemical equilibrium doesn't. That's the important thing.
Okay, so it requires a constant input of energy.
Exactly.
Whereas
If we don't have energy, because we don't have oxygen or we can't use it or whatever the reason, we lose the steady state, we lose life.
yeah, I wrote that down. Life is a steady state process.
Exactly.
Yeah.
That's more important than understanding this.
Okay.
We need energy for that.
You want to use my clicker?
Would be great. Sure. We have one, but in the regular class.
Just when you're ready, just turn
I
it on.
remember me to give it back to you.
Yeah, I'll get it after Professor Santos explains.
Ah, okay.
Slide, previous slide.
Perfect, thank you so much.
That's fine. So, they didn't have any energy, no ATP. So they're not absorbing any sodium. And this number decreased to 50 per se, right?
I was thinking about if the sodium potassium combination not working,
Right. Okay, perfect.
the sodium that normally goes here is not going to be. Remember, this is the one that is taking the sodium out of the cell. So you're going to go from 11 to 50.
Oh, that would decrease. Okay, so then water would go to.
Yeah.
Okay. And then that would decrease. So then wouldn't this triple? Because
That's
the water.
the water is going to move.
Yeah, okay.
Every action has a reaction.
You said electrolyte freely. Is it just the you said
Between the blood and the
in the plasma. So and then for calcium to be released, energy is needed.
no, to be taken back. To be taken back to the
But this one I didn't, I put it together, so I went and tested it over. So for calcium to go back into the small intestine, if long as it is required, I will do this. Different. That's what it
I mean, have it in the Margarita Peruana.
Oh, that's right. Yeah. I'm like, it is. I'm turning it. Yes. All the stuff. Well, yes, that's
Es de las 6. with the day.
But it can be
Work requires 8 components. There are channels specific for water.
So this would be applicable to like glucose.
Glucose well depends. Glucose, there are some cells that normally allow glucose to pass out. Then there are channels for glucose. And some cells that increase. It's not that you have a chance to today we are doing concepts. We are not
I opened it. I read
Let's go back. Remember that this lecture, today's talk is about concepts. We are introducing all the things that we are going to be studying. Okay, it's like a index or table of contents. Okay, it's not necessary that you now take note or learn the examples that we are mentioning. It's simply illustrating, okay, how this is used. Homeostasis is the central topic of physiology. Okay, if you want to summarize in a word what physiology is about, is homeostasis. How the body maintains that. Okay, and there are several definitions, okay, of homeostasis. Some are more simple, more complex. Okay, but it's simply understanding the mechanisms that the body has, all the systems, all the organs together, working together in order to maintain a stable internal environment. Now, there we have another concept. What is the internal environment? Who knows what is the internal environment? The extracellular compartment. You were reading before. the extracellular compound. Okay? And you may ask, what about the cells? What about the intracellular? Of course, cells have also their internal environment, and they have their homeostasis, each cell. Now, if we are going to study the intracellular homeostasis, we have to spend here 30 years, because there is one for each cell type. Now, every cell works in a different way. Every cell will have a different metabolism, different management of glucose or different nutrients, different functions. That belongs to cellular biology, molecular biology, biochemistry. Okay? We like that. We are going to mention that sometimes, but we are more interested in what happens outside the cells. What happens in the blood, plasma, in the interstitial space, in how cells communicate with each other, how one organ tells the other organ, okay, what's going on or what they are supposed to do, how we monitor the variables that we have in the blood, for example, how we monitor the blood pressure, how we monitor the amount of sodium, how we monitor the pH of the blood, okay, the amount of CO2, so we can work, okay? Well, of course, the final goal of this is guarantee or how, okay, that the cells work properly, guarantee intracellular homeostasis. Okay, there are different mechanisms. We're going to be studying them in different lectures. Okay, simply to control the body temperature, okay, control the pH of the blood, the oxygen of the blood, the osmolarity, the amount of sodium in the blood, okay, the amount of oxygen, CO2, electrolytes. Now, in this slide you have several concepts. So this is a very, very important slide. Okay, if you want to study one thing from this PowerPoint, is this slide. Okay, you have there the concept of homeostasis, you have there the concept of internal environment, and you have two more concepts that are regulated versus controlled variable. Okay, what is a variable? Anything that can change and can be measured, can be monitored. Okay, height, weight, age. Okay, blood glucose levels, sodium, potassium. These are things that we measure, okay, that the body is monitoring, trying to maintain them in stable levels. Okay, all the variables that you have there is a table at the end that has more variables, are regulated variables. These are variables that our body tightly, very carefully regulates. Now, not all variables are regulated. For example, if I have a hypoglycemia, I have sensors, oh my goodness, glucose is low. Okay, I release epinephrine, I release glucagon, okay, I release hormones that will stimulate certain metabolic processes, and I will start breaking down glycogen to release glucose into the blood. And I will start converting amino acids into glucose. But that is not regulated. That is simply something that we use to increase the blood sugar levels. Different biochemical, metabolic processes. But we don't have any sensor that tells how much, okay, glycogen we are breaking down, or how many amino acids we are converting to glucose. The same thing happens with blood pressure. If someone has a hypotension, okay, the body has mechanisms to increase the blood pressure. One is producing vasoconstriction, the other is increasing the heart rate. Okay, but we don't have any sensor for the heart rate. The body doesn't have. We do. We have the finger measuring the heart rate, but the body doesn't know the heart rate. We simply use the heart rate, increase it or decrease it, in order to either increase or decrease the blood pressure. That is an example of a controlled variable. You can call it manipulated. Okay, if you study research, for example, okay, you can manipulate variables. Okay, the body manipulates the heart rate, okay, to regulate the blood pressure. Okay. For purposes of exams and so on, simply think: do we have receptors for that? Do you remember any receptor for heart rate in the body? I remember osmoreceptors. I remember baroreceptors for the pressure. We have sensors for the glucose levels, but for the pulse, no. That is a control variable. There you have some examples. Okay, in this case, talking about the regulation of the blood glucose concentration. Notice that blood glucose levels are the regulated variable. We monitor this very carefully because our body knows that if the blood sugar goes down, okay, and it doesn't have to go down too much, okay, we are gonna lose, okay, the functions of the cells. Okay, but there are different variables that we can increase or decrease, but we don't monitor. We don't have any sensor for dietary intake, for the hepatic production of glucose. We don't have any sensor for the output, for the uptake into the adipose tissue. We don't know how much glucose went into the adipose tissue. Okay, we don't know how much glucose went into the muscle. These are things that we manipulate. Glucose is high, put it in the adipose tissue and in the muscle. So we lower, we decrease the glucose. It's low, well, we have to take something sugary, or we have to produce glucose from the liver. We manipulate those variables to contribute to the maintenance of the regulated variable. And of course, we have to study all these processes at different levels. Okay, molecular, cellular, okay, tissue level, organ systems. So depending on what system we are studying, we are going to dedicate more or less time to the cells. For example, in muscular system, we have to dedicate a lot of time to the cells, how they contract, or different things they do. Okay, in other systems, it's not going to be so important. The cells are the structural, functional units of the living organisms. Okay, you know, they can be prokaryotic, eukaryotic. Okay, we have eukaryotic cells, and we have more than 200 types of cells. And that is amazing. When you study the embryology, how from one single cell, the oocyte after fertilization, how that single cell can become more than 200 cells. That is amazing, how they know what they have to do. How some cells become skin, other cells become muscles, other cells become bone. Who tell them what to do? Okay, it's amazing, all that process. Okay, these are structures that are simply bounded by a membrane. Okay, any membrane, any barrier in biology is called the tegument. That's why the skin system, we call it the integumentary system, because it's like a barrier, like a separation. Okay, it's considered a dynamic interface between the intra and extracellular environments. Because it's the thickness. Remember, you don't have to memorize any number there, just simply to have an idea. And it's composed of a bilayer of phospholipids. Okay, that contains proteins, different types of proteins, glycoproteins, when they contain also glucose, lipoproteins, cholesterol, okay, and different proteins that are located. Some of these proteins are simply placed on top or below. They're called peripheral proteins, okay, that are like floating, that you can, if you could separate them very easily from the cell membrane. They are peripheral. And then we have integral proteins that are embedded in the membrane, difficult to separate. Some of them pass through the membrane, okay, and they have different functions. Some of them are receptors for hormones, for different things. Some of them are channels that allow the movement of sodium, potassium, calcium. Okay, they serve sometimes for recognition of the cells. Okay, the immune system recognizes the cells because of these glycoproteins that are present in the outside of the cells. This is why, for example, when we have an organ transplant, there is some rejection from the immune system. If we make a mistake and we give a transfusion with the wrong type of blood, the immune system immediately is going to recognize the red blood cells as foreign. But they are going to destroy the red blood cells. Now, also, there are things that we have to know. We say it's a lipid bilayer, and we tend to imagine that these are simply two layers of phospholipids. Well, there is a difference in the composition. It's not the same type of phospholipids in the outside and in the inside. Okay, is something that, of course, takes a while to study, and we are not going to enter into that, but this is a membrane that is asymmetric, okay, and one of the signals for the cells, when the cells are very old or they are damaged, is that the outer part of the membrane, okay, like turns around, okay, and when that happens, that is a signal for the cell destruction. That's something that belongs to the molecular biology, etc. That is good to know. And it's a membrane that has certain fluidity, okay, and that the fluidity of the membrane depends on the composition, what type of phospholipids, okay, how saturated or unsaturated are the phospholipids that are present there. Okay, so depending on our diet, depending on what we put into the body, we're going to have materials to make a membrane that is more or less flexible. Okay, and of that flexibility, okay, depends the function of the cell. If the cell membranes are very stiff, very rigid, it's going to be very difficult to produce any kind of response to hormones, okay, or, for example, produce exocytosis, endocytosis in a very stiff membrane. Okay, membrane that is flexible, okay, all of the processes are going to occur more easily. And then we have different organelles, okay, that perform different functions, okay, that I'm sure you have studied in the past. We have here an example of a cell in a unicellular organism, okay, and the organ systems in our body, simply for you to see the matching of the functions. Okay, unicellular organisms need to take nutrients from the environment, okay, need to use energy, okay, that they need to process, they need to store in a certain way. Okay, they need to maintain homeostasis, in this case intracellular, because they have a single cell. So they take nutrients, produce energy, they eliminate wastes, different ways. And in many cases they use oxygen, okay, and they produce waste products that may be lactic acid, or maybe alcohol, or maybe different waste products. We do the same, okay, but instead of every cell doing its own things, okay, we have systems that are dedicated to each of these specialties. And of course they work together. As we saw before when we were comparing the functions of the cardiovascular system and kidneys in the regulation of the blood pressure. All of them are working together to perform those functions. Now here we have the cell organelles. Okay, it's not that you have to go back to elementary biology and, let me learn again the functions of these organelles. I want you to study this with a focus on the protein synthesis. How these organelles work to produce different proteins that the cells make. Okay, so you start with the nucleus. Nucleus contains DNA. The DNA that is in the nucleus is the same in every cell. So theoretically, every cell has the capacity of making every protein that we make. Okay, pancreas. In the pancreas you have the beta cells that they make insulin. But if they want, they can produce keratin. And if they want, they can produce collagen. Or they can produce glucagon. I'm a beta cell, but I want to produce glucagon. Why not? No? That's like enlightenment. I have the DNA to make glucagon. Why I should be making insulin all my life? That's what cells may think. Why the beta cells don't make glucagon? Simply because the gene that contains the information of how to make glucagon is turned off. It's like hidden. Okay? The enzymes of the cells that transcribe the DNA don't have access to that area. It's like you have the DNA is like a big library. All the books available. But you have in every part, okay, when you have in every house one of these libraries that contain all the books. But in every house will have access to only 100 books. So they learn about something and they don't learn anything about the rest of the things. That's what happens in the different cells. We turn on and off almost all the DNA except a tiny bit, so the cells specialize in doing certain functions, in having certain shape, in going to certain places, in producing certain proteins. Yeah, I was listening the other day an oncologist, and he was saying, was talking about this phenomenon of cells deciding what to do. It's like, he said, it's like cells suddenly realize that they are free to move to other organs. They are not limited to be in the liver. They can go to the lung. Okay? They can produce other things.
I was going to ask, since the expression of genes has to do with histone, tightening, and relaxing, couldn't we technically develop some sort of therapy that could affect the histone?
Of course.
For like different treatments?
Yeah, of course, yes, but sometimes the therapies, we don't know what they also will affect. Okay? So that's the problem. If you try to create a medication, a drug, that destroys the right ear without damaging the left ear, that's complicated. We don't know what else is going to happen. There are many drugs that when they go to phase 2 clinical trial, they stop. Because they find, oh, no, we don't want this.
It's basically side effects, right?
Eh?
Side effects. The side effects could be very
Yeah, it
adverse.
can be very bad sometimes.
Yeah, like how we discriminate, just
And sometimes you go phase 3 and you market the drug, you start producing the drug, selling the drug, and 3 years later you start having the side effects. Oh my goodness. Yeah, it's complicated. So we study the nucleus. The nucleus has the information of how to make proteins. And I always, we were saying about the library, the huge library with many books. But sometimes you can compare to when you want to cook something at home. Let's say you have a big book with recipes for cooking. Okay, and it's a book that you inherited from your grandma, you inherited from someone. You don't want to damage the book, and you don't want to take it to the kitchen because it's gonna get damaged there. So you make a picture of the recipe, okay, how to make this, John or something, okay, and then you go with the cell phone, the picture to the kitchen, and you cook. Okay, that is more or less what is the function of the RNA. We want to make insulin. Simply take the information of the gene that has the instructions of making insulin in the form of RNA, take it to the cytoplasm outside the nucleus, and the ribosomes will take care of reading that information in the RNA and making the protein, simply by attaching different amino acids together. That is not the end of the story. Okay, ribosomes simply put together the amino acids. Then this chain of amino acids has to go to the Golgi. Okay, in the Golgi, it's not going to go alone. It's going to have some company. Some proteins that are called chaperones. I take the protein there so nobody touches it. Be careful, be careful. And in the Golgi, we fold the protein. We add sulfur, we add this, we add lipids, we add different things, making glycolipids, glycoproteins. And we tag, what is this going to? Okay, this is going to the blood. Okay, send it outside in the vessel. Oh, this is going back to the nucleus. It's an enzyme for transcription. Oh, this goes to the mitochondria. This stays here. That goes to the cytoplasm. Okay, so try to make that story, okay, of how the cells make proteins. Okay, what is the chain in that factory? DNA, RNA, protein, then modification of the proteins. If any step here fails, okay, disease will occur. Because if let's say I make a protein that is 1,000 amino acids long, and I send the protein to the Golgi, and the Golgi has to produce like coil. And one of the enzymes that make that coil is not working. So I can make the coil, what I will have is something weird. If the protein doesn't have the proper shape, it can't be exported. So what the cells do is, okay, leave it here. Let's try another. Weird shape. Let's leave it here. Another. And at the end of the day, I have a ton of misfolded proteins. And cells can't do anything else because now the organelles are like this and the garbage like this. Okay, so accumulation of misfolded proteins, which is the basis of many diseases. Okay, pancreas will produce diabetes, and the brain will produce Alzheimer's disease. Okay, it's something that pathologically speaking we call amyloidosis. Okay, accumulation of proteinaceous material. Okay, that is the basis of many chronic diseases like Parkinson, diabetes, type 2. That is because it's very hot, no? Let's see, maybe they left.
It's also the story of the animation and the story of the origin.
They will lower the temperature.
Professor, have you heard about the comparison of diabetes to Alzheimer's and how it technically could be called type 3 diabetes?
I was thinking about that, I didn't say.
Can you expand on that? Because I've seen some things about it, but I haven't dug
Okay, the
into it.
cause, nobody knows the ultimate cause, okay, of these conditions. There are mutations, okay, there are variants in the DNA that predispose to Alzheimer's, predispose to diabetes, predispose to Parkinson, and there are some variants that like protect people, okay. But in those who are predisposed to Alzheimer's, for example, the risk factors, okay, behavioral risk factors, etc., that produce diabetes, like lack of exercise, chronic inflammation, stress, overweight, etc., produce also the same risk factors for Alzheimer's disease. So in some, that is not official, but some people call Alzheimer's disease diabetes mellitus type 3, okay, because the pathophysiology, the mechanism for the accumulation of these plaques in the brain is the same that for the accumulation of the amyloid plaques in the pancreas. In the pancreas we call it amyloidosis because when we secrete insulin, we also secrete another enzyme, another hormone that is amylin. Insulin goes to the blood, amylin stays there. Accumulation of amylin produces amyloidosis, damages the pancreas, and people develop diabetes. But a similar process happens in the brain. We don't produce amylin, but we produce other proteins that produce Parkinson, produce other types of dementia, like frontotemporal dementia, like other and Alzheimer's disease.
Insulin resistance as well.
Insulin resistance is very important in this. But there is a lot more to it. That's why you don't see many people talking about this, because that's still starting.
Beginning.
Yeah, it's the beginning. Now you have an idea of how to prevent it. It's not doing Sudoku when you are 70. No? But then we have the interstitial space. There's really not too much to study here. That is simply an illustration. When I studied histology, first year of medical school, for me the interstitial space was like a river around the cells. No? It's like water there. Substances flow from the blood vessels to the cells and they reach there. No. There are many proteins and many compounds, organic compounds, hyaluronic acid, okay, glycosaminoglycans, different glycoproteins, and that is another field of study. Okay, and that field of study is so important that many theories about diseases, they state that diseases actually start here in the interstitial space. Okay, when something goes wrong in this area, okay, any of these links, any of these proteins or glycoproteins that attach the cells in their place, that bind cells to the blood vessels, that hold the basement membrane or the epithelial cells in their place, when something there goes wrong or you have accumulation of any wastes or any toxins in that area, that's the origin of many diseases. that now we say we don't know the cause. Of course, we are going to know in the future, or maybe we never know. Okay, it's very difficult to study certain things because we can be experimenting with kids to see how everything starts. Okay, I'm going to take a sample of your interstitial fluid every day to see changes. There is a theory that we like a lot in medicine. There is a black box theory. It has nothing to do with the black box of the airplanes. And it's simply something that works very well. Okay? You need to judge when it works, when it doesn't. For example, when I studied medicine, and we studied the pancreas, this was the lecture. Blood sugar levels increase. Beta cells detect that. Something happens, and they release insulin. And insulin binds to receptors in the cells. Something happens, and sugar goes down. Do you think that with that knowledge you can practice medicine? Why not? We were practicing medicine then. Perfectly. To treat a patient with diabetes, you simply need to know, okay, what type of insulin, what is the amount of units, depending on the carbohydrates, exercise they do. Should you know those secrets? Yeah, it's very nice to know these secrets, of course. But it's not totally necessary. When you need to know that? For example, when you're going to change the medication that you're going to give to the patient. Okay? If the patient is taking metformin, and suddenly metformin is not working, and you're going to change to another medication, you better investigate a little bit. Because maybe that medication is the appropriate, maybe it's not. Okay? In those cases, it's important. That's why we don't enter too deep into these mechanisms that belong to the cellular, to the molecular biology. We only use them, we borrow them, and we use them when it's necessary for practicing medicine. That's why we call this course clinical physiology. Okay, in some points and sometimes we're going to go deep into the concepts when it's necessary for clinical practice. Sometimes we're going to use the black box theory. Okay, this happens, then this happens, then this happens, because it's not necessary to know anything deeper. Okay, and if you try to go deeper in some of these areas, you're going to create noise. And that noise may prevent you from learning the things that you really need. Okay. So here we have a couple of concepts more: cell division, cell differentiation. This is not difficult to get. Cells divide. Have you noticed that biology is the only science where division and multiplication is the same? Bacteria divide, bacteria multiply. You always obtain the same result. Okay. Cell division is simply when you produce two cells from a single cell. Can be mitosis, can be meiosis. When you produce two cells from one. Okay. Notice that here, for example, in mitosis, you have two daughter cells that are identical to the parent cell. You can start with one, and you can have millions of cells. If we talk about bacteria, that those millions can happen in 6 hours because bacteria divide very fast. Okay, human cells take longer. But the important thing is they are identical. Cell division. For example, if someone has a wound in the skin, a small wound, you're going to produce cell division of the cells of the epithelial cells, and we're going to have identical cells. Now, another thing is cell differentiation. Okay, cells divide, but they become something different. Okay, that doesn't look like the parent cell at all. Okay, one example of this is what happens in the embryological development. Okay, we start being a single cell, then we have cell division, 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 division. All of the cells look alike. They are not alike, but they look alike. They have differences in the genetics. Some genes off, some genes on. Okay, there is a moment when this group of cells that we call the blastocyst, okay, will take one of these three pathways, either to the ectoderm outside, or to the mesoderm in the middle, or to the endoderm inside the embryo. Okay, so the ectoderm is going to give origin to the skin and nervous system. Okay, the endoderm inside is going to give origin to the gut, for example, liver, pancreas. And the mesoderm, the middle, is going to give origin to connective tissue, okay, to, for example, muscle cells, red blood cells, bone marrow cells. And they have different degrees of differentiation. Once a cell, let's say, imagine that these cells can make decisions. Okay, what do you want to become? I want to become ectoderm. Once they are here, they can become anything. You can go to the skin, to the brain, to the spinal cord, nerves, but you can't become a blood cell. There is a commitment. Once you differentiate, there is a commitment. Now, cells, as they grow and differentiate, they are every time more and more and more committed to one function. Okay, if someone is, say someone is 75-year-old, and they have been a software engineer, and when they are 76, they decide, I want to be a ballet dancer. Too late. Too late. Okay.
That's why when you're a child, you're more prone to learn things quicker.
And you like all the jobs that you find. I want to be a policeman. I want to be a pilot. I want to work at the zoo. I want to be a vet. Kids want to be everything. Once you are older, maybe you also want. But no. You could, but you have to give up many things to study again. Let's say, I want to play classical piano. I have to stop working, dedicate 8 hours per day to learn piano. That's not possible. So as the cells get more and more committed, we're gonna be changing the name. For example, the oocyte, okay, after the fecundation, it's called a totipotent cell. It can do anything, totipotent. Okay, then the cells, okay, when they are more committed, they become pluripotent. Still, they are capable of becoming many types of cells, but not everything. Then we have the multipotent and unipotent. They can be only one thing. Okay? We're going to be studying this. Remember, you don't need to study this now. Okay? We're going to apply this, for example, in hematopoiesis. And we have a hemocytoblast, the stem cell of the bone marrow. It can take two lines, either the lymphoid or the myeloid. If you decide to go to the lymphoid line, you can become a lymphocyte. And that's it. If you take the myeloid, then you can be a red blood cell, a white blood cell, or a platelet. There's more diversity there. Once you decide to become a red blood cell, there is no going back. You don't even have a nucleus. So what are you gonna do? You're simply a bag of hemoglobin. How do you want to become a platelet now? Okay, that's more or less how it works. We are gonna stop here, and we are gonna continue tomorrow. Okay.
Okay.
You're welcome.
Is this material the Ganon's book?
Is there?
The textbook that in the syllabus, the Ganon's Review of Medical Physiology, is
That book is great because it's very summarized everything. It has practice questions.
so, but is it chapter 1 that we're covering right now?
I'm not sure if that's the chapter 1 of the book. Just look at the topic. Okay. But I don't think there is a chapter for today's lecture because today we is introduction. Okay. Just concept. Okay. I don't think you're going to find these into one chapter. This is like scattered there. Sorry, no, we are not sure yet. We don't have vision. I don't know. We're not actually
Yeah? Okay. But it will be like one for you and one for professor. No, we need to I just didn't know if your questions will be on her side or
in the exam, yes, but not
Did I open all of them?
That's why
thing that I remember, you know that you sent out? No longer in the drive regarding the ChatGPT, because I remember reading that paragraph.